very happy to have Pierrick BOUSSEAU from the University of Georgia. He is telling us springs and monetary geometry.
Okay, so thank you very much for the introduction, and thank you very much to the organizers for the opportunity to give this series of lectures. So each of the lectures with you will have some slightly independent focus, but I hope there will be some general themes which will be visible. And roughly the first two talks will involve some real symmetry, and the last two talks will be more focused towards enumerative geometry and some quadratic lines. The title of today's Brains and Non-Correct Geometry. It's a reference to a paper written by Anna Nung and Rafa, which is called Brains and Toric Geometry from 1997. And this talk will really should be viewed as a kind of generalization concept. In the first part of this talk, I will review the non-toric story. And the main content of this talk will be what do we do when there are marginal brains which correspond to some non-toric geometry. And this what I will be talking about is contained some joint work with Valery Alexeyev and Ilya Agus, which is the archives of the master. So the goal of this talk and of this paper is really to answer some question which is monetary phrased in some physics context. The general physics context is geometric engineering, which involves producing some quantum field series out of string theory. And for the purpose of this talk, the kind of quantum field theory we care about will be 5-dimensional quantum field series. So whatever they are physical theories living on a 5-dimensional space-time. And the fact that this thing should even exist was a surprise in the mid-90s. By standard quantum field theory reasoning, maybe you don't expect to find quantum field theories in space-time dimension strictly more than 4. But in the mid-90s, it was realized from string theory construction that such things actually exist. And in the physics literature, there are two main proposals for how to construct such things, two main constructions. So the general idea is to start with a string theory, which is something very complicated, living in very high dimensional, like 10 or 11 dimensional space, times in which contain gravity is very complicated. And what you want to do is to extract from this higher dimensional quantum gravity theory a much simpler subsystem. And one way to do that, so there are essentially two ways. One involves singular geometry. And so what would be relevant for us here, you can start with something called M theory, which is something living in 11 dimensions. And if you want to produce something in 5 dimensions, you can consider 11-dimensional space-time to be R5, times something of lower dimension 6, and you can take this thing to be a Calabi-Yau threefold. I will return it by X bar. So Calabi-Yau threefold. And the idea is that if the space becomes singular, there will be some physics which will be localized near this singular point, and the corresponding physics will be described as something living on R5 times this singular point, so you get some 5-dimensional theory. And so for the purpose of this talk, this Calabi-Yau threefold will be non-compact, and it will be singular. So X bar will be a singular guy. And so technically you will look at some canonical threefold singularity. So you should think of this X bar as some kind of local picture around a singular point inside the Calabi-Yau threefold. And you expect that this non-trivial singular geometry produce some interesting 5-dimensional theory on the short reservoir.
If the singular locus is not a form, then you can simplify them.
So these canonical threefold singularities might not be isolated. They might have some 1-dimensional pieces, but still it's allowed. And this case what you get is not some kind of 5-dimensional theory coupled with some higher dimensional stuff. So actually for this talk, the singularity might be isolated or might not be isolated. Otherwise. But indeed, if you're really some purely 5-dimensional system, you might want the singularity to be isolated. So it's one way to produce some localized theory, start with some singular geometry. The other way is to consider intersecting brains. And here, the thing which will be relevant for us will be type 2B. String theory. you live in a kind of trivial geometry, simply R10, so the geometry will be trivial, but in this geometry there will be some interesting physical objects, these branes, and when these branes intersect, if they intersect along a common R5, there will be some interesting 5-dimensional theory of this common intersection. So I'll be more precise in a few minutes what kind of brane I consider, but it's a rough idea. There is two ways to localize, to produce some localized theory, either by considering some singularity in the geometry, or considering some very easy geometry, but some non-trivial physical objects. And the general question we might want to ask is, can you compare these two constructions? And the kind of direction we will explore is that if you start with a system of branes, you will construct a 5D theory that way. And you can ask, can you construct the same 5D theory using M theory on a non-compact singular Calabi field? The kind of mathematical question would be, given this system of branes, which often will have some combinatorial looking description, can you produce some interesting non-compact singular Calabi field? And for a particular class of branes I will review, the answer, this is Hannah and Vasa paper, the answer will simply be a toric Calabi field. And for more general class of branes, the answer here was unknown, and it is what I will explain with this paper. So the plan of this talk would be, first of all, to review the toric story. And then explain the non-toric. So I need to be slightly more precise. What do I mean by this intersecting branes in this type of B-string theory? So we need to know a few things about this type of B-string theory, but not much. What we need to know is that inside the theory there are so-called PQ5 branes for any P and Q which are a non-zero pair of integers which are co-primed. And in the standard physics terminology, if it's a 5 brane, it means it will span a 6-dimensional submanifold of your space-time. And we'll consider the space-time of that 2D string theory to be R10, which is some R5, which is an R5 where the 5D theory will try to construct relief. And then we'll write times R2 times R3. And so we'll consider our PQ5 branes. So they're supposed to be 6-dimensional, and I want them to have a common 5-dimensional intersection, because I want to construct a 5-dimensional theory. So I'll put them on R5 times something 1-dimensional inside this R2. And I will put them on the line of slope PQ inside this R2. So here is the picture. I will draw the picture of this R2. And I have a special point in my R2, which will be the origin. And this requirement here is required by the symmetry. If I want to preserve enough symmetry, you want the PQ index of your 5 brane to match with the direction of the line which is spanned by this brane. So here's an example. I might consider some 3-1 brane, so I just look at the line of direction 3-1, this is R2. I look at another one of direction -3, 1. And I look at two of them of direction 0, -1. So I can have two PQ5 branes for the same PQ. So in this case, it's like they're on the same ray, but with some kind of multiplicity. And in the physics story, if you want to get some kind of supersymmetric configuration, you have a charge conservation condition. You want these vectors in R2 to sum up to 0. So the sum equal to 0. Okay, so mathematically, you just have this picture. You just have a bunch of vectors, integral vectors, summing to 0. In the physics terminology, the thing is called a web of 5 branes. And so on these R2 pictures, these lines intersect at a single point. And the 10-dimensional geometry, this single point has a transverse R5, and the expectation is like localized around this point, there is some interesting 5-dimensional theory that physicists care about. And now the question is, given this construction of the 5-dimensional theory, can you get to 1 not from rings but from singular geometry? Can you find some x bar so that if you consider M0 and R5 times x bar, you find the same theory as the one given by this picture? And this thing is an answer which has been is a question which has been answered around in the 90s, late 90s.
So that 2 times.
Sorry?
Come up. So that 2 times the 0.
Yeah, that's right. So here I put 2 times. Sorry?
Oh, the question is 2.
Yeah, that's right. You can think about it as being some multiplicity attached to this picture. And in this picture, it's necessary because I wanted balancing, so I have 2 other, like I have 1 and 1 in the vertical direction. So here I have 2 times 0 minus 1, you will be minus 2. Balance each. Yeah, that's right. I guess the physics would say you just have 2 fibrils of the same charge on top of each other.
Just the remaining R3 factor is any.
Sorry?
Just the remaining R3 factor for the angle.
It will play some role in some moment. At this point, it does not play a role. It's kind of trivial. The chance of the trivial R3 sequence. So somehow out of this picture, there should be a way, if you believe that this thing has an alternative description of M0 and the Claudius threefold, there should be a way starting from this picture to produce the Claudius threefold. And so I will first give the answer for how to do that, which is some simple looking toric geometry. So I will first give the answer, and then explain how the answer is related to mirror symmetry. But in the non-toric situation, there will not be an easy way to guess the answer, but we'll guess the answer by going through some non-trivial mirror symmetry. So first of all, what is the answer? If you have such picture, there is a natural notion of dual polygon. So essentially for each of these arrays, you can look at some normal integral direction. So I will start with some integral point, and this 3, 1, if you look at, so for every pq, I will take the normal vector to be minus qp. So the 3, 1 will become minus 1, 3. So 1, 2, 3. So here is the vector minus 1, 3. Minus 3, 1 will become 1, minus 3. Is like that. And finally, 2 times 0 minus 1 will become 2 times 1, 0. 1, 0, 1, 0. And exactly because this vector sum up to 0, if I do this construction, I get a closed polygon. So I end up by P is lattice polygon. And once you have this polygon, you can look at the cone over this polygon. And let me see what they do. Yeah, minus 1, minus 2. Yeah, that's correct. Okay. So this picture lives in some R2. And you can think of this R2 as living at height 1 inside some R3. So I will consider R2 times 1 inside R3. So the R2 is something like that, and there is this polygon inside it. The origin in R3 is somewhere here. And then you can take the cone over this polygon. You will get some 3-dimensional polyhedral cone. And this 3-dimensional polyhedral cone, you can do it as a fan of an affine toric variety. This is a 3-dimensional cone. And so it is a fan of a 3-dimensional affine toric variety, which will be the x bar we're looking for. This cone, if you have a fan consisting of a single cone, it's an affine toric variety. And if this cone is like non-trivial, then this thing will typically be very singular at the torus fixed point. So let me say a few more words of what this toric gravity looks like. So this cone has a natural projection onto r greater or equal to 0, which is just an height function of this cone. And this thing is a fan of A1 of the complex line. So there is a natural map of fans, so there is a natural map of toric gravity, so the gravity x bar, map to C. And if you try to visualize this map, so here the complex line, you will find out that if you look at the fiber of a point which is not 0, the fiber is a copy of C star squared. And if you look at the fiber over the origin, you get something whose picture is essentially the web picture here. So this picture here will essentially be a polytope picture of the fiber over the origin, meaning that the fiber over the origin, in this example, would have 3 irreducible components, each of them being an affine toric surface whose corresponding polytope is given by the cone in this picture. So there's these 3 cones, they define me 3 affine toric surfaces which are glued together to give me the central fiber that will be denoted by x0 bar, the fiber over 0 of this geometry. So one way to think about this x bar is starting over 0 with this reducible union of toric surfaces, and then get a smoothing. They smooth to the geol fiber, which is just a C star square. Okay, so it will be important for later. As this 3-dimensional geometry, I can think about it really as the total space of the one parameter family of surfaces. Here I explain how to create this x bar, which is the non-compact singular Carter 3 form we're looking for, this x bar. And so you can not only describe the singular geometry, but you can also describe its resolution, or precisely its Crepont resolutions. And the claim will be that these Crepont resolutions are essentially one-to-one in correspondence with triangulations of your polygon, more precisely so-called regular triangulations. So for example, here I could take the following triangulation. So if I really want the resolutions, I want a triangulation as fine as possible. So whose all triangles are made of lattice triangle of lattice size 1, as of this example. And so why is it true that such picture produce a resolution? In the same way I took the cone over the original picture, I can take the cone over that. And now we'll get a fan, which consists of many cones, and it will define me a toric gravity x, which is no longer affine, which naturally lives over the singular variety x. And if you ask what this geometry looks like, in particular what the fiber over 0 looks like, you should look at the dual of this decomposition. So here the dual will look something like that. And this dual, you should think about this as being a perturbation of the original web that I've erased. The original web was consisting of this picture, and you should think of the blue picture here as being a perturbation of the original picture. Asymptotically, if you look from very far, you see back this picture, and you have the 5 grains are being separated in the middle. And the claim would be that if you look at the fiber over 0, so here the x bar 0 was looking like that. And the claim will be that the fiber over 0 of the resolution will look like this kind of perturbed one, meaning it will look like that. And here you can see that here this thing will be the polytope of a compact toric surface. This consisting of a polytope of another compact toric surface, and both of these surfaces will be contracted by this morphism. And this is complicated singularity here, you obtain from this smooth geometry by contracting a bunch of compact curved surfaces. And there are many ways in general to triangulate the polytope, which correspond to different combinatorial ways to deform the brains, which correspond to different ways to take a curve resolution of this singularity. So now what I want to explain is the relevance of a mirror symmetry. So in particular here, I just gave the answer. I just claimed that if you took with this picture of 5 brains, somehow the answer, what is a dual absolute Carlos threefold, is given by this recipe. But I now derived it anyway. And to do that, I want to make a comment about a mirror symmetry. So in this story, there is a Calabi threefold X bar with curve resolutions. And you can ask what are the mirror of these Calabi threefold. And because here everything is toric, it shows the answer just given by toric mirror symmetry. And the point of toric mirror symmetry is that it's essentially combinatorial. It essentially reduces by changing the fan and polytope pictures of toric varieties. So here we have this polytope P. And previously I was using this polytope to hook up a cone, and then I was using this cone as a fan of a toric variety X bar. But instead of using this P as a way to construct a fan, I can just try to use this P as being the momentum polytope of a toric variety. We're claiming that by toric geometry, this P naturally corresponds to some YD, which is some projective toric surface, and coming with a line bundle L, which is actually an ample line bundle. Another way to say it, each time we have a projective toric variety equipped with an ample line bundle, there will be the corresponding momentum torus vibration over some base, and this P is the base of this vibration. So otherwise, so this picture here is really a picture of YD, so this is D will have 3 irreducible components corresponding to 3 sides of P. And the interior of the polytope corresponds to the C star squared living in my toric surface. So here, Y minus D is simply the torus. And if I want to make really concrete what is the relation between this ample line bundle and this a polygon, if I take F, the Laurent polynomial, into my both X and Y, with Newton polygon F, the Newton polygon F equal P. So I take monomials in X, Y corresponding to integral forms of this polygon P. And if I look at the vanishing locus of this polynomial, I will get some affine algebraic curves inside C star squared. And the claim is that this curve naturally compactified into the toric variety Y, and the resulting curve is defined by a section of this ample line bundle. It lives in the linear system of this ample line bundle. So actually, so this thing is a curve in C star squared, and if you add the divisor at infinity, you get a compact curve inside your joint point that I denote by C, and this curve lives inside the linear system of the ample line bundle. So out of P, I took up the surface with actually a curve in it. But if you want the mirror of x bar, which is threefold, you might expect this mirror to be another threefold. And the recipe of toric mirror symmetry is telling you that the mirror of x bar will be the non-compact cardinal threefold and not by Z, which is defined by the following equation. The actual surface inside C2 is coordinate V times C star squared is coordinate xy, while F is the normal polynomial as above. So there are four variables for an equation, so the thing is threefold. If you try to picture this threefold, it has an obvious map to C star squared, which is projection of xy coordinates. And inside this C star squared, there is this curve. And if you look at the fibers of this map, if you look at the fiber of a point which is not on the curve, you get UV equals something non-zero. So the fiber will be a copy of the C star, which topologically looks like a cylinder. But if you look at the point on the curve, you get the equation UV equals 0. So you get the union of two lines, which topologically looks like a kind of cone like that. So the circle here is shrinking. And so you can think of Z algebraically, geometrically, it's like an affine conic bundle over C star squared, which is degenerate over this. Now you might ask, what is the relation between this geometry and the original web of fibrates? So somehow, if I want to justify the relation between the web of fibrates and the geometry x bar, I claim it would be easier to first get a relation to this geometry and then apply your symmetry. And so what is the basic relation? The basic relation is that to pick a triangulation, like above, pick a triangulation, is like picking a large complex structure degeneration of a cis geometry. So in particular here, P is a polytope of Y, and if I triangulate P, I triangulate the polytope of Y, which means there will be a one parameter degeneration, because G1 fiber is Y, and this fiber of 0 is a union of toric varieties whose polytopes are the various pieces of this decomposition. And actually, so if you look, the fiber of 0 will look like this decomposed picture, whereas the original Y looks like that. And actually, if I decompose into triangle of size 1, the triangle of size 1 is a polytope of simply P2 with a line bundle of 1. So my surface R is break into a union of projective planes. And if I look at my curve C, which is my curve C inside the Y, it will break into a union of lines in these various P2s. Many lines inside these P2s. And if you look at the dual intersection complex of these lines, you will get this perturbed web of fibrates. So you will get this blue picture. It will be for each vertex. You will get some irreducible component. So in other words, what I'm trying to say is that this picture is a tropical curve, which is a tropicalization of this curve C with the limit of the curve C will degenerate in this way. It's the same as that. And this thing,
one enjoys everything.
you mean here? Yeah, that's right. This thing is supposed to be a picture of negative 0. That's right. So this thing is an algebra geometric way to understand this picture to say just the dual complex of what happens with spatial fiber. Or if you don't want to go to the spatial fiber, you can do some more traditional picture of maybe tropical or tropicalization. You can think of C star squared as being like R2 times T2. And think of this picture as being the base R2 So at every point there is some kind of T2 fiber. And the curve lives inside the 6R squared. And you can look at its projection inside R2, you will get the amoeba picture of algebraic curves. And these tropical limits, these amoeba will attract onto this tropical curve. So in other words, since algebra, this curve covers the Riemann surface near this tropical limit, there is some kind of thickening of this curve. So here there is a quite direct way to go from the combinatorics of this graph to some geometry. If the algebraic curve come out as a kind of thickening of the graph. And you can go through a sequence of string theory dualities that I will not review to indeed argue that the 5-dimensional theory you care about, which is first defined as a system of branes, if you compact it of a circle, we'll have an alternative description in terms of this kind of called Z, where the curve turn into, where the web of branes turn into these geometries. The branes turn into geometry and some string dualities. So you get the Z which appears, and then you apply your symmetry to get the X bar you already want. So the plan for the second half of the talk is to start with a more general system of branes. And our goal will be to find the kind of M3 drawn out of threefold. Because the situation will no longer be toric, we will not be able to guess the answer. Instead, what we'll do, the first step will be to produce an analog of this Z, the analog of this YD, the analog of this threefold. And then you can claim by going through the same chain of string theory dualities that what we really want is a mirror of this threefold. The question will be reduced to the question how do you find the mirror of the kind of non-toric version of the Z. Because things will be no longer toric, there will be some non-obvious question. Let me come to the non-toric story. So, in the first story, in physics of wedge, we start with type 2B string series, and you consider intersecting fibrings. But it is known since the late 90s that in type 2B string series there are more type of branes. In type 2B string series, in addition to PQ fibrings, there are so-called PQ7 branes, which are also indexed by a pair of co-prime integers PQ. And there are 7 branes, meaning now they correspond to some 8-dimensional submanifold, okay, 10-dimensional space. And what we'll do is to, as before, to consider R10 to be R5 as R2 as R3. And as before, we'll consider some bunch of fibranes on R5 times some kind of graph inside R2 times just the origin in R3. And now we'll add to this picture some PQ7 branes. So I need 8 dimensions. So I still want a common 5-dimensional because I still want to define the 5-dimensional set here, so it takes R5. But now I will take the 3 remaining dimension to be this extra R3. So that the 7 branes will sit at a point inside this R2. And for this picture to interact with the previous 5 branes, you need these 7 branes that I will represent by red crosses to be some points at which 5 branes end. So here there is a number of rules. The general rule is that if you have a PQ 5 branes, so some line going in the direction PQ, then it is possible for it to end at some PQ7. The PQ here should be the same PQ here. So here is clear what PQ means mathematically, just the slope of this line. you can ask what is the meaning of the index PQ for this point here. The point will be that the 7 branes is not just a point in R2, but it's a point which introduces some singularity for the natural integral affine structure of this R2. So actually I will draw this cross with some kind of dot. Because this dot, you should think about it as being some kind of cut. And when you go around this cut, there is some non-trivial matrix with Sn2z, so the matrix MPQ in Sn2b, which is a unique quantum matrix in Sn2z which live invariant this PQ direction. And you should think of this thing as being the monodromy for the singularity of the integral affine structure. And this kind of singularity, the simplest kind of singularity you can have sometimes is called focus. So here is a kind of new picture we'll consider one of these webs. And I will take the web which is dual to partial decomposition of my polytope. I will consider this triangulation, which is dual to a picture like that, where here are some integrity 2. And what I will do is introduce the 7 branes here, and I will introduce the 7 branes here. And then physicists will claim that if you look at such picture, then if you consider the corresponding system of branes, it defines some 5-dimensional theory of this R5 factor. Yes?
Why couldn't you talk about 7 branes in the toric case?
So the point would be that introducing 7 branes will correspond to some non-toric geometry. So the toric theory is that if you only start with 5 branes, it will correspond to some toric geometry. If you include 7 branes, it will not be able to include that by staying inside toric geometry. It's somehow exactly the kind of main point of this talk, that if you have only 5 branes, we know the answer for what is corresponding to the freeform is given by toric geometry. If you include 7 branes, it was known since the late 90s that the answer could not be given by toric geometry. So it has to be given by some space. And the point of this talk is to try to give the answer to exactly this question. So somehow we start with this picture and want to produce a possibly non-toric geometry. So actually it was known already in the late 90s or early 2000s that actually not every such picture is physically consistent. So not such picture. And I'm not going through the details of the reasoning. But the idea is that you can start with one such picture. So I always consider a picture where there's this kind of blue web, and then I put on 7 branes like near infinity. But you could try to go from one such picture to another one by moving one of the 7 branes. So for example, you can try to move these 7 branes along this PQ direction. And when it happens, when it crosses a vertex, we will need to do something non-trivial, because of this cut, this direction here, when you go through the cut, is no longer the same direction as before. And so there will be a rule, essentially the number of 5 branes ending on these 7 branes will be determined by the condition that this new vertex you should have a balancing condition. You still want to have a balanced picture, but in the sense of this integral affine singularity, including this cut. There will be some rule for how to change the picture when the similarities go through. And then to get a picture looking like the original one, you can try to rotate this cut, the monodromy cut, and you change the picture according to the monodromy to get a new picture like that. So there will be some story starting with such a picture. You get some symmetry through, you get a different picture. In physics literature, this thing is called dynamic whip and move. And it was observed that if you start with a random configuration, when you do these moves, you can end up with a graph where some edges have negative multiplicities, which in the physics language means you have a non-supersymmetry, you have some anti-brain. So the picture will not be supersymmetric, and so the picture will not be consistent. So there will be some restrictions, some non-trivial restriction. If you start with this picture and if you do all possible dynamic Whitman moves, you should always get some positive numbers. And only for this one do you expect to have a corresponding geometry. These are the only ones which are physically consistent. So already it is showing that the story will be kind of non-trivial. So some of these consistency conditions which appear in the physics story, they should appear in our mathematical geometry way to produce the geometry. So to construct the corresponding X bar, our first step, as I announced, would be, because we would not be able to construct X bar directly, our first step would be to construct the analog of this, toric surface YD, which is line model L. And once we know that, we can ask what is the real object. Question would be like, so what is the analog of before YD was the toric surface with the line model. We could use the line model to look at this curve C to look at this threshold C. This is the first question. So starting from such a picture, we should satisfy this kind of consistency, such a complicated looking consistency condition. So here is a recipe. So if on this picture you forget the red crosses, just a blue picture as before. So there will be a dual polygon, which is drawn here, and so there will be a corresponding toric geometry. So if you just look at this polygon, as we explained before, there will be a corresponding toric set, y bar, t bar, n bar. Just toric. And somehow introducing the red crosses should correspond to some non-trivial modification of this toric geometry. And here is a recipe. So each red cross is a point where some ray is ending, and each ray corresponds to some toric boundary divisor on my toric surface. So for each red cross, I will look at the point of the corresponding toric divisor, and I will blow up this point. So here I will blow up this point, I will create an exceptional T1. Here I will also block, and here I will also block. So for each red cross, I block the point on the corresponding toric divisor. Y is the block. R, this is covered. And the key point is that this point are contained on the toric boundary, but they are not torus fixed points. So this is operational like non-toric blocks. Y is not a toric line, you know. And I will take for D the structural form of D bar. So D in this picture will still be the union of these three Y points. And suddenly this pair YD is non-toric if you look at the complement Y minus D, given by U is no longer right?
So the second rate also not.
Sorry? Yeah. So until now I have not used this data of the multiplicity. I will use it in one moment to say what is a line bar. So to get the geometry, I'm not using the multiplicities. The multiplicity will be used to say what is a line bar. Or equivalently what is a curve I'm looking at. It's the geometry. Okay, so what is U? So one way to think, so here I just claim to think is the right answer, if you want to convince yourself what is correct, in the curve picture, C star square was a kind of a trivial topologically the T2 bundle over this R2 picture, the way we're living. And now this geometry U over this picture where I have the 7 grains. You can argue that topologically it would be some still generating 2 formation, but there would be some singular fibers over points corresponding to 7 grains. Because this U will have some so-called almost toric fibration over this integral affine manifold similar, which is also a topic of the contributed. Okay, so in particular, like topologically, if you think about the other characteristic of U, it is a number of 7 grains. Certainly it's not the star square, which is another characteristic.
So the red bottom line is
Okay, so in C's way to start the story, the red lines do not intersect. But in 1 minute, we will start moving around the singularity. That's something more interesting to my pattern. So I told you what is YD, now what is L. So L will be the pullback of the toric line bundle. And I will subtract to it the electron divisor notation. I will subtract MI, EI, where the EI as the exceptional curves and the MI as the multiplicities. So the multiplicities will be exactly the intersection numbers of my curve with the exceptional divisor. So here, I will look at the curve which looks like that. Intersect C exceptional at 1 point, 1 at 1 point, but C exceptional divisor at 2 points.
so why not follow it?
Yeah, so the claim is that it will just will be that C's picture corresponds to that. And it's in the key point that here there is this leg of multiplicity 2 ending on a single 7 grains, which is different of having 2 legs of multiplicity 1 ending at different 7 grains, which would correspond to going at 2 different points. You see that exactly this process of the single multiplicity ending here means you can actually separate, you can no longer separate the 2 brains. So before it was possible to separate them, but not because they end on the same 7 brains, they are kind of stuck together, which corresponds to the fact that there is a single exceptional divisor. Okay, so from such picture, we explain how to get this YD. So this YD is an example of what is called a locked labial surface. And we produce the line bundle of it. Now you might ask what about this strange consistency condition in the physics language. So here there is a theorem we proved in our paper, which is that you get this consistency phrased in terms of positivity of multiplicities in all the way to quantify the web is equivalent to a kind of natural positivity condition of this line bundle L. We want essentially L to be does non-negative intersection for every curve in the geometry. So in the toric situation, if you have a polytope, you automatically produce an encore line bundle. But here, because you take something toric and subtract something, and if you subtract a lot, your line bundle will no longer be encore, will no longer be F. There will be no curve in the linear system. But the claim is that the right consistency condition is a kind of natural notion of positivity of this line bundle, it should be F. It's a kind of theorem that this condition of being F is equivalent to some combinatorial consideration, which I'm going to do in this situation. And furthermore, we argue that once your line bundle is F, it's like positive enough to have a smooth curve in the linear system. So in this case, we can show that then there exists a smooth curve. And then we will have a picture which is completely analogous to the toric situation. You have a surface, and if you look at the complement of the boundary of a non-compact holomorphic symplectic surface, which contains some smooth curve. And once you have this picture, so you want this view containing this smooth curve, then you can look up some z, which as before will be some integral affine bundle over this geometry, which is degenerate over the difference is that now since z leaves over versus u, no longer fits this squared. But apart from that, it's the same construction. Z is a non-compact Calabi sphere. And now the claim is that if you go through the chain of string dualities, the claim will be what we want, the x bar we want, is the mirror to this non-compact Calabi sphere. So the x bar we want is the mirror. And because z is kind of built from this log Calabi surface, this is not bundled, and by that we talk about mirror actually.
This is the definition of this is a physical claim.
So, okay, so for why this x bar is the correct thing, this thing is a kind of physical claim. That starting with this collection of 5 lines with 7 brains, if you go through the sequence of string dualities, the claim that you get the equivalent description in terms of the z, and if you apply your symmetry, you get the expected, the kind of last step of string dualities, you get the x bar you should.
Is there some physical property that
So definitely, yeah, so it's a good question, like, so this duality between the web and this Calabi threefold should have non-trivial, there should be non-trivial prediction.
yeah.
And I think it has not been explored, but it's definitely something which should be explored. For example, for toric Calabi threefold, we will topological vertex formalism to calculate we have a peak invariance, sometimes in terms of data which is good. And so for this non-toric guy, if you have a geometry or peak invariance, it should be similar like vertex, topological vertex formalism involving these two guys with these similarities, for example. Like one example of mathematical prediction.
So is the red box somehow also related to the look like?
No, I think they're really different. So for example, both brains exist in the toric geometry.
Yeah.
And in the toric case of this toric, there is just no red dots. So these red dots are really something which only appears to go beyond the toric situation. So of course, in this geometry, there should be some analog of Each buffer. And then we might ask everything we know about the geometry for this geometry. Yes, these red dots are really the kind of new indicators. So I will just end by trying to explain how do we do your symmetry. So how do we construct our x bar? So first of all, let me say a few words about what x bar should look like. So in the toric situation, x bar was looking like the one parameter family of surfaces. Generically, it was something smooth, and then there was some kind of union of surfaces. And if I look at its preference resolution, it was some kind of union, like normal crossing union of various surfaces. And then the total x was some kind of smoothing of this fiber from zero. Zero, something zero bar, and something zero. And the basic strategy, so what we really want to construct is x bar. First of all, we will not construct x bar, but we will construct some x, and then claim we can contract things. We construct the Williams resolution first. So first we will construct x. And to do that, at the first step we'll construct x0. To do that, we'll construct the central fiber, x0, so it's a normal crossing surface, and then argue that there is a way to smooth out this normal crossing surface to get a solution. And then get x by some deformations. And here this second result is only analogous to the result of Friedman in the context of K3 surfaces, which tell you if you have a normal crossing union of surfaces, which look like a singular version of the K3 surface, then you can smooth it into an honest one parameter family of K3 surface. And what we prove here is the analog of this result, but which has a different proof because the geometries here are non-compact, so it's more subtle. But roughly the point here there will be some deformation theory. So So what I would like to focus on is how to describe the central fiber. What is XZ? What is this normal crossing union of surfaces? And in the toric situation, we know what to do. So in the toric case, we were looking at some decomposition of the polygon. And then we're looking at the dual web, and this dual web is actually a picture of the polytopes corresponding to various components of my X0. So I want to do something similar. So I'll start with a picture like above. And somehow I would like to interpret this picture as being a union of irreducible components glued together. So if there is no red dot, I know what to do. For example, this triangle corresponds to some compact toric surface. And in the example I've been working on is, you can check this thing is actually weighted per unit space, P114. With a cyclic singularity here. And here there is like 3 non-compact components. Now the question is, what do you do when you add this red cross? How do you modify the geometry? And the main thing, which is that if the picture is consistent, this is line bundle is F, then there exists a way to push 7 points inside. So you have no 5 points is attached to the 7 points. So you start with such picture that you don't know how to interpret geometrically, and then you push the 7 brains inside, and when they cross here there is some natural rule, and here if you apply the rule you can check that once it is inside it is no longer attached to any blue part of the picture. And the blue edge which are here also disappear. And so actually the blue line here, which looks like it's bending, actually becomes a straight line if you take into account the window journey through the cut. And the same thing here. So and here if you do the calculation, it's also the case here. So this thing is a non-trivial statement, and actually the process of pushing the 7 points, the could intersect, the cuts could intersect, is quite complicated. And the claim that this statement is some kind of, well, I will not explain. If you are interested, you will ask me about it afterwards. It's some kind of mirror to the sequence of flops in a maximal degeneration of this YGN. So we have this lock at the surface with an F-line bubble, which is obtained by blow-up or something toric. And you can consider the toric degeneration, and then do the blow-up. But on the central fiber, the line bundle has no reason to be NEF. But by minimal model programs, so here there is some kind of MMT. There will be a sequence of flop which makes your line bundle NEF at the end of the day. And this sequence of flop is mirror to this operation of pushing the 7 brains until they are no longer attached to everything. So I could say more is interesting. And once the 7 brains are inside, now the claim that each of the components you see can be interpreted as a geometry. So for example, here I see this thing, this blue thing with 3 singularities inside, but no longer attached to anything. Now each of these things, for example, for the picture, can be interpreted as a base of the almost toric vibration. On some log canadian surface, so symptomatically there will be some geometry. So if it were toric, the geometry would have a T2 vibration over the interior of this polytop. But there is a non-toric geometry, so that over the interior of that there is 3 similar fibers. So So syntactically, this thing is related to the work of Symington, and for our purposes, we explain how to produce a series-pairs algebra geometrically. Starting with this singular toric variety, doing some deformation theory, you produce this kind of non-toric pair. So for each face in this picture, you interpret it that way, and you get your surfaces, and then you glue them together. This thing is your x0. And then so once you have your x0, you apply some deformation theory to produce x. And then you need to prove that inside your x you can contract essentially every compact curve and every compact surface to get the singularity x bar. And the claim that this x bar is the geometry we are looking for, because the existence was somehow predicted from the brain-web picture and the sequence of dualities. Somehow we give some algebra geometric construction. As a final comment, so it's a story. Related to the kind of question, essentially any statement you know about toric mirror symmetry, you can ask it in this context. So here there is a prediction, this is x of this is x bar, this is x are mirror, this is z, also you can work on the surface. So every statement about mirror symmetry, like enumerative mirror symmetry or homological mirror symmetry, you can ask all of them for these pairs of non-compact threefold, and most of these statements are open. We did not construct it since geometry before, so we have a new set of like non-compact threefold, which is a kind of almost version of the toric threefold. And so every question or every result you might know in the toric situation, there should be a version. This is not toric. And I will stop here. Thank you very much.
So first question, in this example, instead of, what you could also do is you could like blow up 2 times, right, on the bottom face,
Yes.
and then you could move them together. But I guess moving them together doesn't change anything.
So it kind of does. So
Okay, that's my question then. What does it change?
yeah, so like having the 2 points separately would be like considering maybe decomposition like that. Is correspond to bring 2 points. So essentially the limit of bringing 2 points is like bringing 1 point twice. Yeah, so I think it will take a few minutes to explain. But roughly there is some kind of geometric transition. If you take the 2 points together, you block twice and you create an A1 singularity. And then you could resolve these A1 singularities. And then if you do the appropriate contract, and then if you can contract something else, you recover the geometry I was talking about. So there is some kind of parational geometry type relation between the two, which on the mirror side has to do with this kind of non-toric deformation of the complex structure. So there is some connection between these two, between having 2 different and one thing of multiply 2, but it's actually not obvious in general.
So this is on the one side, this is a parational.
Yes.
On the like local your surface side, that's a parational.
Yes, that's right.
And on the
mirror side, it's like a deformation of the complex structure.
deformation. Okay. Thank you.
Yeah, and it's actually very important. Like, actually, in the physics literature, what was really difficult was the case where the multiplicities are not one. Like, what was difficult is the case of multiplicities which are not one. It's not possible to just say we split it into something. It does not work. It's more interesting.
And maybe if I started, so this is just we already have explained it, but if I start with a toric case, then, okay, yeah, I think you already explained it. Sorry, I was just yeah. Thank you.
So when the physicists introduce this system, what are the questions they are asking? What kind of things they want to find?
And so definitely, so one question they were asking was, so what is the corresponding Cardinal threefold? And one reason to care about this Cardinal threefold is that in physics language, each time there is 5D theory, This, from a physical point of view, there is an important quantity which is called free potential, which is like the constant term in the usual cohomology, which involves triple intersections of divisors. So if you have a kind of Calabi threefold, to calculate the object physics curve is very easy. You just calculate you calculate triple intersection of divisors. But if you just have this web mixture, it's unclear how to get such numbers. So actually, currently we are discussing with some thesis, which is like applying our geometric PCB to get out these numbers. Yeah. So actually, there are many other things you might ask about these things. For example, they have some X branch, this 5D, X branch, which are kind of object which are this really near symmetry. Okay, it's part of the X branch. These are like many good questions.
Is your freeform related to the mirror of the top-liner surface?
Yeah, that's so. If you just think about the non-canonical surface and think of its mirror as being another. So roughly the G on fiber, so our threefold. The point is that the G on fiber, is a mirror to just a non-canonical surface itself. In particular, because we're in dimension 2, there is this kind of coincidence that there is a mirror topologically the same. So there is a G on fiber here. Actually diffeomorphic to the original order-rotating by use, the line lines. So there is a compatibility with like purely two-dimensional symmetry.
And once you know the general fiber, is it immediately determined the secret of the sigma?
No, the thing actually does not. So in the G-on fiber, like even in the toric situation, the G-on fiber is always C star squared.
Yeah.
So really like for the point of you need to pick a curve inside C star squared. And then it's mirrored and shows from C situation. So here it's exactly the same. So instead of C star squared, this is U. And for every chose curve in U, you have one situation.
Another question. How do you know you're going to have the deformation space is one-dimensional on the side?
Yeah, so this kind of one parameter deformation is kind of mirror to the line bundle L on the other side. So the line bundle L on the side of ideal is in the direction of the Keller space. It's mirror to this one dimensional